Cassie. Today I'm going to be telling you all about how you can make your own art with Rust. Anytime we've got just art on the slide and there's no citation at the bottom, that's one of my pieces. Most of them are all Rust. So, I'm Cassie. I'm extremely on Twitter. And you might recognize me by one of those two avatars there. I started making computer art like this in 2013 on a Raspberry Pi. And I started using Rust in 2014. While I was getting set up for this, I actually found one of my projects to learn Rust, which was a ray tracer. I tried to build it to get you an image for this talk. It was from Rust 0.10, so everything was very different. I did a lot of learning, reading people's articles online about different techniques you can use to make a piece of art and doing stuff from scratch, like just grabbing an image and setting all the pixels. A lot of stuff I learned was from this blog here by an engineer named Inigo Quiles. But I had to do lots of things from scratch and set it up every time. So for this talk, I tried to create pixel canvas, which you can just use and very simply declare, like, make me a window that I'm going to draw in, and let me mess with this image and make a piece of art just without having to deal with all the windowing and setup for different platforms. Before we can make art, though, we've got to look at some of the basics, like images. So in the image, we've got a grid of pixels. Pixels are colors. You've got dimensions and coordinates to describe what each pixel is. We can declare that with the type something like this. You have some storage that describes your data, and you've got extra data about that. For each of those colors, we have a type like this with red, green, and blue parts, and we describe each of those colors just with numbers. If you're not already familiar with this, you can always just look up a color picker, just Google it, and you can get the numbers that you need when you're getting started. Now, if we want to make a piece of art, we need to decide how we're going to start approaching that. One way here is this gathering technique, where you take each pixel and you say, what color should this pixel here be? So we take an image, and we can loop over it, and we can set all the pixels. I've got this image dereferencing into just a slice of pixels, so you can do all the kinds of iterating and combinators that you're used to working with in Rust. So for instance, you could take chunks that are the width, and that lets you get one row at a time. Or you could use enumerate, so you have all the positions of all the pixels on the screen, which you can use to control exactly what you're drawing at that point. And maybe we stick an array in there to pick what colors we're going to be using. And then just with a few more lines of code past that, I can stick it in a window. We've got an entire little application demo right there. Actually, will make you a window. I can jump over to one I've got right here. A little bit more customized for me. So we can take a completely different approach to rendering, where instead of saying, I've got this pixel, what color is it? We can do the opposite, and we can say, oh, I have a color here, where are we going to put it? This image back here is taking lots of different samples and sort of spreading them around the screen and letting them fall where they may. So here, we take an image, and we index into it with some coordinates, and we set those colors. Maybe we loop over a circle, make it with sine and cosine to decide where things go, and mess with different colors. Or we go and look on Wikipedia and find a formula for a spirograph and then loop over that. This again, we can just add a few more lines of code. Particularly here, I add a little bit that lets us grab the mouse position, so we can make an interactive piece of art. Responds to where I move the mouse around. Got a spirograph that as I move the mouse around the screen, we get different patterns and spikes and circles. So you can play around with something that you control. Now with those basic approaches, you might want to take a more interesting piece of art where you're going to make a bunch of creative decisions with it. So to do that, I'm going to build up some of the toolbox that are really useful for an artist working with just basic pieces here. First step, we're going to take blending. So we can take two colors, and we can assign them sort of to ends of a spectrum of colors. And then you can grab points in between those. So in between red and blue, we get purple. And you don't just get one middle point, you can take any point in between those. So if we want to have a smooth blend somewhere in our art, we can use this. We also might want to take ranges and change how big they are or like what direction they're pointing. For instance, you might want to grab the width of your screen in pixels and turn it down to some smaller number, like a float 0 to 1 for your control. And this doesn't just get the end points, you get the points in between and points outside, sort of matching the lineup of that. Give you restricting here, which is you might have used max or min to cut off some range of numbers at the top, but I always forget which end is which. And it's nice to have some syntax that makes it clear where your value is going to finally end up. Here, maybe you've got some positions and you have some dangerous value that would break your math, so you just stop it before you get to that point. Often when we're working with geometry, we want to take vectors. You can think of them as arrows or pairs of coordinates, and you can add them either by laying arrows end to end or by adding each of their individual components of that. Either way, this gives you the resulting vector. You can do other things like take a vector and multiply it to get different lengths, or some other more exotic operations like the dot product. You take two vectors and you multiply the matching parts and then add that all together. This might seem a bit arbitrary, but it turns out that this gives you something that lets you measure the angle between two vectors. And so if they're pointing in the same direction, their components sort of add together and you get a large number, and if they're pointing at right angles to each other, they cancel out and you get a 0 or a small number. When working with geometry in space, we like to be able to describe things like the surface. What direction does it point? We call this a surface normal. And if you want to say light a sphere like this, you take those normals and you take the direction towards the light. And then when you take the dot product, all of the surfaces that are pointing towards the light are bright, and the ones that are pointing away are dark. And then we want to restrict this because we don't want negative light on the far side. But taking some of these tools and putting this together, we might want to render. So we can take a scene like this and we take some perspective into it. We might call the eye or the camera. We want to find out what we want to show. One classic way to do this is ray tracing, where you find exactly where you hit the scene if you look in some direction. But this can be a lot of complicated math to do properly. A much easier approach is this technique called raymarching, where instead of finding the exact point, you take a bunch of small steps forward and see at each point, am I inside the ground yet? Or have I hit a thing yet? And that gives you an easy way to tell where you are. If we want to start here with the camera and firing rays, we've got a bunch of points on our screen, and we want to find what direction each of those should go. As a first approach, we can just let's look straight ahead first. Let's pick some direction that's forward, and then we can add in a little bit of extra. So for a given point on the screen, we use some numbers to, like, if it's on the left, our thing points a bit to the left. We do that for each of these points. And then as one last step, just to clean things up a bit, we do this operation called normalizing, where we divide them all by their length, so they're all the same length and pointing out neatly together. Using this general approach, you can see we're looping over pixels here, so we're gathering, and we're picking the direction with our camera, and then we're doing some rendering to tell what to say. Our raymarching is like we showed in those diagrams a moment ago. We take a direction, and we step forward. We check if we're under the ground, and if we are, we return a hit that says where we are. If we're not, we take a step forward again. That height we can just describe as a function on the ground. So at any given point, flat, we can say how high up that is. And our rendering, we just use that marching, step forwards. If we hit the ground, if it's close enough, we return a ground color. Otherwise, we return the sky. And all of this together gives us the world's most complicated way to draw a green rectangle and a blue rectangle. But we do it this way because this is a really nice setup to start adding more things to it. So for instance, we've got the distance, So now we can use that to blend between colors, and now we've got fog as we go into the distance. Or maybe we jump over to our height function, and we change our formula. Multiplying some sines and cosines together gives you a bunch of nice bumps, and as you just add things together and play around with that formula, you get more interesting patterns. I'm going to jump back to the rendering. I'm going to pull out what color the ground is, so ignoring the fog separately. We can start doing stuff like, let's get the height of the ground and let's multiply that up. So as you're low down, you're darker, some depth to the world. Now the sky is starting to look flat, so we can take the sky, use a dot product to say what direction are we looking, and then use that to blend between a nice sunset color and a sky blue. And maybe I think this looks a bit too bright, so I'm going to just add in a few little spots there, add some numbers that make things look better. Lots of this is deciding what you don't like and then just tweaking in different places until it looks like what you want. We can use more dot products. I showed using the dot product for lighting in that example earlier, and we can just take that here. We take the normal of the point we hit. We just take the dot product with some of the, like the direction of the sun. And if we step back and forth, you can see we get a lot from that lighting change there. I didn't mention how we ever calculate that normal. That's because this is actually probably the most complicated thing in this whole scene. But you can do like I do, and I just went and I looked up, hey, how do I calculate the normal for the ground? So whenever you're stuck, or if you have some idea, you can see and find someone else who's done it before you. So I'm just going to do one last change to our height here, just adding a bunch more pieces to get a more interesting scene. This is just layering more and more things on top until it looks cool. But you'll notice as we get steeper and more complicated here, we're starting to get these weird stripes. And this is the disadvantage of raymarching. Often you'll step too far while you're checking, and you'll get these regions that it thinks they're all the same distance apart because they stepped the same amount too far. But luckily there's a really simple way to fix this. When you hit something, you take one step backwards, and you try again smaller. You keep doing this until you've got a size you're happy with. So if we take our marching code, we can just add 4 lines in here that say, if we're still too big, let's take one step backwards and try again with a smaller step. And just adding that makes the ground much smoother, gets rid of a lot of those rough stripes. Let's get into the last piece of polish. So we can take the color here, use an if expression to say, some of this is water, some of this is sand, based on how high up you are. We can do really subtle stuff like, it's hard to see, but in the mountains in the distance, we've got rock and snow at the top. Or we can take the light, and we can reuse our raymarching. So at each point, we can just step towards the sun. If we hit something, that means we're in a shadow, and if we don't, we're out in the light, in the sun. And maybe now the shadows are too dark, so we add secondary lighting coming in from the sky. Or stuff like we take a bunch of different steps in different directions, slightly random directions, and that makes our shadows softer. And so we can do this here, taking some idea and getting a framework that lets you start exploring and playing around and start working through all these different variations, getting more and more detailed and things that are expressing what you want to show as you go. And actually, let's see what we've built here. Okay, here we go. Ta-da! But you might notice that took quite a while there. If you're just going straight forward, you want to make a piece of art that you're going to make lots of images with, or if you want to build something interactive, it can be frustrating to work with something that's running that slow. So we want to take our art, and we want to be able to take some idea and make it faster, make it run better. So for this demo here, I'm going to work with this fractal called the Julia set, partly because it's beautiful and it's interactive, and also because it's a small enough demo that we can look at all the changes we want to make for performance's sake. The first step is we take the complex numbers. We describe them in terms of a real and an imaginary part, and they work a lot like vectors. You can add them together. What's different is that you can also think of them as these angles and lengths, and this lets you multiply them. And the way complex numbers multiply is this spinny thing where their angles add together and their lengths multiply, and so you get all these spirals heading off in the distance. But this is something you could just, if you need to use them, you can look up how to make them. And in this case, it ends up being a few dozen lines of code to build one. Now, if we want to make the Julia set, we can use this spinny fact of the complex numbers. You can take some point C that's going to describe what it looks like, and then each point on our window, Z, we just repeatedly square it and add our number and square it. And so the spinning sort of folds it over, and then we shift it and fold it over, and this adds up all these wrinkles and complex parts. And then we, based on how each point travels, if it stays close to the center, then we can color it one way. If it runs away, we can give it different colors based on how fast it's running away. In code, you can see again, we're looping over, so this is gathering. And we've got this loop inside for each point. We want to square it and add, and square it and add, looping and keeping track of how it behaves. And then we, like we said, if it stays close to 0, we color it black. If it diverges, runs away, then we color it based on how it acted. Now let's take a look at what that ends up doing. So we've got this beautiful, like fiery, spiky fractal here, and we've been forced to go to a bit lower resolution here, but when I was working with this was often take like 500 milliseconds to render. You can maybe see in the top. So this would be really hard to aim pointed at the spot you like. So this might not be fun to work with interactively, so we want to speed this up. And the first approach, somewhat magically, with Rust, I can say the easy thing to do here is threads. That's not something you say usually, but so here I grab rayon and I chunk it, so each of those rows can be passed off to a different thread if it wants to. So this is the only change I need to make right here. And this alone gives us one that is running in 40 milliseconds. So this is already running 3 times faster. And on a resolution like this would be early enough to stop. But if I want to run it on my computer, this is still taking like 200 milliseconds to render. So there's still got some rough spots. So if you've got something that's really tough like that, you might need to jump into some other changes. So the second approach we can try to speed this up with is SIMD. SIMD stands for single instruction, multiple data. And so with the normal approach, if we want to add a list of numbers like this, we've got to add them one by one. With SIMD, we can take those 2 lists, and we can use a single operation that adds some big chunk at a time. On my machine here, we can do 4 of those operations on a float at a time. With other types, you can get more, and with other kinds of machines, you can maybe do wider as well. So if you're thinking about how you're going to speed up your code like this, you might look at your complex number and say, oh, that's a vector. I can see there are 2 floats, and we're adding them both the same way. So what if we just try to define it so we used a SIMD type and did 2 floats packed together there and just added them together? This is what I thought like a while ago would be the clear way to do this, because it's sort of the natural thing to do. But this ends up not being what you want to do. For one, it's only 2 wide and you can't get any better than that. And also, there are some operations that don't clearly work like this, like the multiplication ends up a lot messier. But luckily, the thing we do want to do is just as simple. Instead, we make our complex number just before complex numbers sitting next to each other. Now, our add stays exactly the same in some other operations as well. Of course, some things we have to change a bit, like we change some types when we're calculating the length, or we use a different comparison operator so we can get 4 booleans instead of 1. But overall, most of these are sort of minor changes that are driven by your types. When we're working with a row of pixels, instead of working 1 pixel at a time, we grab a chunk of pixels that matches the width we're working with, and we run our code over that. So your loop is going to look something like you've got 4 lanes that are all doing the same work at the same time, looping and doing their changes. And so far, this is all great, but unfortunately, it's a bit harder. If we want to have something like breaking early in our loop, then we need to be able to have our lanes run for different amounts of time. And this doesn't exactly match the we're always doing the same work on each instruction, so we need some way to deal with that. The way we approach this is we add our own variable that keeps track of what loops are done. I've got this div variable that means diverged, so things where that's true are done running. Then since the only thing we're using at the end of our code here is the number I, we're able to just change the way we add I. So we add 1 if it's still running, and we add 0 if it's not running. Then we just break if they're all running. So this gives us the effect of we're adding 1, and then when a thing finishes, it stops making changes. You could also use SIMD to pack all your colors together and store that in one go, but that ends up being a lot of juggling types around, and I found when I was prototyping this that just pulling out each part at the end once you finish doing the hard math and doing it one at a time still works fine and gets you enough speed. All of these are available, so if anyone wants to try to do the SIMD version as an exercise, you could try that and see how it works. So I'm running it SIMD here. In the middle, we're even faster again. This is running about 4 times faster, not 3. And stuff is beautiful and smooth. As one final show, you put those two together. And this is even faster again. This is running almost 10 times faster than our first version with those little changes we had there. So, what's the takeaway? Where do you go from here? I hope some of you make your own art. I want to see what you make, and if you do something with any of this, please send it to me on Twitter. You can work with the pixel canvas crate I made for this to get started really quickly. And you can look at some of the places I learned, like Inigo Quilis's blog to learn the details of raymarching and lots of different tricks you can do with that. Or look at Shader Toy, which isn't Rust, but lets you do some of these same kinds of tricks online in shaders. And that's what I have for you there. Thank you.